Hello everyone. Let us discuss about stability of systems, based on which the systems are classified into stable and unstable systems. An arbitrary relaxed system is said to be stable system, bounded input, bounded output system, if and only if every bounded input produces a bounded output. Let us consider x of t be the input to a continuous time system, CT system, and y of t be the response of a system, that is the output for x of t. Bounded input refers to the condition that finite value of the input for any value of t for this matter. So when you say bounded input is bounded, then there exists a constant, say for example mx, such that the modulus of x of t will be always less than or equal to a finite value mx, and mx is always a finite value, it is less than infinity. You can ensure that this is true for all values of t. Okay, so bounded input signals could be of step signal, examples, or I can say decaying exponential signal e power minus at, and even impulse signal is also considered as decaying exponential impulse signal are all examples for bounded input signals. We can talk about unbounded signal, particularly unbounded input signal or ramp signal, increasing exponential, are all examples of unbounded. Bounded output refers to a condition that there exists a constant my, such that the modulus of y of t is always for all values of t less than or equal to my, and my is always less than infinity for all values of t. This is true. Bounded output refers to finite and predictable output. Finite and predictable output at any value of t. So in general, the test for stability of a system is performed using some specific input. Upon applying the bounded input to a system, the output is also bounded. Then the system is said to be declared as bounded output stable system. We'll always think about it. So let me consider an input signal to a system, CT system, which produces an output for a specific input. We'll check the nature of y of t to know whether it is stable or not. For an LTI system to be declared as stable system, we have some conditions. The condition for Bibo stability can be transformed as a condition on impulse response. For a Bibo stable system, LTI system, CT system, the integral of h of t modulus of h of t dt must be a finite quantity. So this is called stability condition to be fulfilled for a system to be declared as Bibo stable system, because we know that the output of response of any system for an input x of t will be obtained from the convolution of input and the impulse response. So when you expand it, it will be x of t minus tau d tau. Okay, so by taking the absolute value on both the sides, the equation modulus of y of t will be equal to modulus of integral minus infinity plus infinity h of tau into x of t minus tau d tau. So when it is confined to individual variables, it is with respect to h of tau multiplied by x of t minus tau d tau, or you can even express it as modulus of h of tau into modulus of h of x of t minus tau d tau. If the bounded input is bounded, then there exists a constant mx such that modulus of x of t minus tau will also be a value less than infinity, right? So the equation of y of t, modulus of y of t, could be written as, it's a constant, so tau varies from h of tau into d tau. We can say that the output is bounded if the impulse response satisfies the condition. What is the condition? The condition is integral minus infinity plus infinity modulus of h of tau d tau must be a value less than infinity. Tau is a dummy variable. So you can go for changing the dummy variable and redeclare the condition. The condition for an LTI system, CT system to be stable, Bibo stable, the condition is transformed in terms of the integration condition with respect to h of t or h of tau. You can test the stability of a system whose impulse response is given by h of t is equal to e power minus 5 into modulus of t. For stability, so imagine that there exists a system whose impulse response is h of t, whose input is x of t, and response is y of t, where h of t is known to me, it is e power minus 5 tau. Check whether the system is Bibo stable or not. So given that h of t is equal to e power minus modulus of t, for stability I need to check the condition, so it must be less than infinity. We just go for this condition verification. In this case, h of t dt, which is equal to minus infinity plus infinity e power minus 5 modulus t into dt, which will be equal to simply, in our case, e power minus infinity to plus infinity, because modulus is useful if it is a complex number. E power minus 5 modulus of t is an absolute real value. So I can go for minus 5 modulus of t into dt, which can be broken into two conditions. One is over the negative interval minus infinity to 0 e power 5t dt, plus the other one is 0 to infinity e power minus 5t dt. When we evaluate this, we will find out that it is e power 5t divided by 5. Lower limit is minus infinity, upper limit is 0. Here in this case, e power minus 5t divided by minus 5. Lower limit is 0, upper limit is infinity. So when we expand this, e power 0 divided by 5 minus e power minus infinity divided by minus 5 plus e power plus infinity divided by minus infinity divided by minus 5 minus e power 0 divided by minus 5. When you start evaluating this, you will find out 1 by 5 minus 0 plus 1 by 5, which is equal to 2 by 5. I am sure the integral minus infinity plus infinity modulus of h of t dt is a finite constant. Therefore, the system is stable. Another problem, given that h of t is equal to e power 4t u of t, check whether the system is stable or not. We apply an input to a system h of t whose output is determined as y of t. If you start evaluating, where h of t is known to be, it is e power 4t u of t. So when you start checking the condition, modulus of h of t dt, which is equal to integral minus infinity plus infinity modulus e power 4t, right, u of t into dt. Since u of t is present, I can convert the integral limits to 0 to infinity, right? Yes, e power 4t u of t. Modulus doesn't have any role to play in the case of real valued signals. So I can say that integral minus infinity plus infinity modulus of h of t dt reduces to 0 to infinity e power 4t dt, which will be evaluated as e power 4t divided by 4. Lower limit is 0, upper limit is infinity. So e power infinity divided by 4 minus e power 0 divided by 4, which is equal to infinity minus 1 by 4, which is equal to infinity. Since the integral minus infinity plus infinity h of t dt is not less than infinity, it is not a finite value, it is infinite. Therefore, the system is unstable system. Agreed. And we can have one more example, probably little bit tough to handle. For example, given that h of t is equal to t into e power minus 3t u of t, check whether the system is stable or not. For stability analysis, I have an integral minus infinity plus infinity modulus of h of t dt must be less than infinity. So when I start checking modulus of h of t dt, I could say that it is minus infinity to plus infinity modulus of t into e power minus 3t u of t dt, which is equal to modulus. There is no imaginary and real part, all of them are real valued variables. So modulus doesn't have any role to play. Since t into e power minus 3t u of t is involved, it is converted into 0 to infinity. T into e power minus 3t dt is the variable. So how will you evaluate it? Integral minus infinity plus infinity modulus of h of t dt, which is equal to integral 0 to infinity t into e power minus 3t dt. Yes, how will you implement it? So when you start implementing integral u v integral uv. So u multiplied by integral v minus integral within braces du is to be taken first and integral v is to be put up next. So you can think about it. In this case, t into e power minus 3t divided by minus 3 is the first component. The second one, integral du, t is u, du is 1, and 1 multiplied by integral v, it is e power minus 3t divided by minus 3 with respect to t. Lower limit is 0, upper limit is infinity. So this integration will result in minus infinity into e power minus infinity divided by minus 3 minus e power minus infinity divided by 3 or 9. I'm sorry. So and you can say that the third value will be 0 into, when you start applying the lower limit, minus plus. So obviously this will result in 0 multiplied by e power 0 divided by 3 plus e power 0 divided by 9. So the answer will be which is equal to minus infinity multiplied by 0 divided by 3 minus 0 plus 0 plus 1 by 9. So the total value will become 1 by 9. If you start evaluating it, integral minus infinity plus infinity modulus of h of t dt will be a constant finite value. Therefore, the system is said to be stable. Thank you.